Welcome, howdy. Let's go again. Let's go again. A few more hours of live streaming. Beaming, dreaming, and live streaming. More hours of live stream. Okay. Yeah, that's good. Okay, this seems to be working. Right. So we'll get right into it. Okay. I'm gonna skip this question. I don't know when I come back to it, but one day I'll come back to it. I have an idea for a solution, but I didn't want to implement it. It's too messy of a solution. So we'll start with this one. We'll start with this one. Try to go for 4 hours today. See if we can get there. Valid binary strings with cost limit. Given two integers n and k, the cost of a binary string s is defined as the sum of all indices I zero-based, such that s of I is equal to 1. Okay. Binary string is considered valid if it does not contain two consecutive 1 characters. Its cost is less than or equal to k. Return a list of all valid binary strings of length n in any order. Huh. So I'm given n and k. I've got to get the valid binary strings that don't have consecutive 1s. Could have consecutive 0s, but not consecutive 1s. And it's the total number of 1s is less than or equal to k. Okay, interesting. Okay. Huh. So another way of expressing this is how many ways can you distribute a 1? Well, I guess for each one, how many values of n and k are there? N is relatively small and k is also relatively small. It's interesting that k is that. Oh, excuse me, it's the sum of the indices. I'm sorry. Oh, okay. So it's not the sum of the 1s, it's the sum of the indices that contain a 1. Okay. Well, all right. So a few things to say here. This can be brute forced. So n is small enough where you can just generate all the strings. You could literally just generate every binary string and then check if its cost is less than, just check those two conditions. 2 to the 12th in binary strings is, it's only about 4,000 or so. So you could check this very directly. Yeah. Do they want a list of strings? Okay. Okay. All right. I think bit set to string. I think you can do just a 2 string here. All right. Well, we can just do this, brute force it. There's no real reason to try to figure out how to do this more efficiently than that. So we're just going to brute force it then. All right. So first check is going to be J0 bit 1. J is less than 32. Oh, I should do better than that. Can I do it like this? Let me just check a couple things. Whoops. I think I could do event is 3. Then we're looking for 111. 2 to the third is 8. Yeah, this is fine. This works. Yeah, that's fine. Okay. We'll say consecutive equals false. If consecutive, continue. This could be could do 1,000. It's probably fine. Might have to do one reallocation every now and then. I could do 4,000, but 1,000 is probably fine. It's a good heuristic guess. All right. And then we're going to say if it's consecutive, then we continue. Otherwise, we'll save the cost. Actually, let's just do it this way. If not consecutive and total cost is less than k, is it less than or less than or equal to? If it's not consecutive and it's less than or k, then I'm going to result that pushback. Fairly confident you can do stood bit set and actually you can do this. It's 32 of I, 2 string, and then we just want the last 8 characters, just substring. Which I think, let's actually do this way. Const string, bin string. Just convert it to a binary string. Then stood string last stars. Bin string, substring. Yeah. We're gonna move that. Stood move. This is gonna be substring, bin string of size minus n character, something like this. Yeah, okay. Actually, they're only going to be at most 12. I don't need 32. Okay. I want the last characters and characters of the bit string used as subjects. See what it says. I think that's it. Oh, no. We do need to check consecutive, so we'll say previous next. Previous equals false. So say if I and bit, then previous equals true. If previous, then consecutive equals false. A few things. Oh, I do need the index still. Okay, that's annoying. All right. They want this 0 indexed. It's ended up being more complicated than I thought it was going to be. Okay, the 0 based there. So if we have this bit, then we increment the cost set previous to true. Otherwise, previous equals false. I mean, sure. And I think this is going to get optimized by the compiler, by the way. Something like this. I could have the code slightly wrong. So this was my output, their output. Oh, oops. Okay, got it. That's subtle. It's going to be n minus I plus minus 1, I think. I think it's either minus 1 or plus 1. It's inverted. There you go. Okay. All right, let's go with a few other. Let's go with like the longest, the largest one. Let's do 5. Let's do. K could be pretty large. What did they say? It could be like 140. They minus 1 or plus 1? I think they said minus 1 for the triangle number. So it's not exactly a triangle number. It's related to triangle numbers, but not quite. Those are technically triangle numbers, but they're smaller. So it's going to be 12 times 11 divided by 2 is 66. Yeah, 66. And then let's do like 2. Let's do like a smaller. I guess substring was correct. That was what I was checking. Let's do like 20. All right. Just try a bunch of cases just in case I made a mistake. Correct and standard approach. Okay. Mm-hmm. Oh, I don't need the n at the end. Okay. Oh, all right. 0 to 15 only. Number 6. Oh, I didn't calculate that correctly. So in my substring, I mean this will I think this gets optimized by the compiler. Oops. This section gets optimized by the compiler. I don't need this n here. Okay, it's probably correct. I'm gonna go for it. Yeah. Slow though. Oh my gosh, is that slow? Oh man. Oh gosh. Yeah, I don't really feel like thinking about it so hard to figure out what I'm sure there's a better way to do this. Let's see. Let's see what the AI says. I don't want to waste too much time trying to figure that out today. I don't want to waste too much time figuring it out today. It's reasonably fast, even brute forced. I actually thought it was gonna be faster than that, but I guess it's not the best. It's okay. Actually, no, I could do. I could just look at the solutions. Oh, none of them went 0 milliseconds? I'm sure there's a way to do it in 0 milliseconds. I'm sure you could do it in 0 milliseconds. Critical bug. Critical issues. Fixed bit set size. Incorrect bit iteration. Uh-huh. It's unclear. Okay. Uh-huh. Implementation is correct. Given n is less than 12, and k is less than equal to n. What did they say? They said this isn't clear. I mean, they could just cast. It's fine. Logically correct. No consecutive ones that cost k. You just tell her it's correct, and it's like, you're right. It's such a pushover. Although it's not a total, I shouldn't say it's such a pushover. Sometimes it can be really stubborn. It kind of depends. But if you're actually correct, usually it'll figure it out pretty quickly. Just gotta tell it a few times. Okay, recalculates every iteration. I actually optimize this. Iterating by index is slightly cleaner. I kind of like this. I don't do this often enough where I bit shift by index. I should do this more. Yeah, I should do this more. I don't do this enough. Yeah, let's do that. I actually like that a lot. I'm gonna go submit it again, see if I get a better score. No. Yeah, I should take a look at the solution. Oh yeah, I don't do that often enough. I should do that more. Mm-hmm. Yeah, it's a little bit cleaner. Let's try this one. I do like that a little bit better. Yeah, that's substantially. I don't do that enough. For some reason, I don't default to like. I should bit shift to the right and use and one. That's a much cleaner way to do it. Hope didn't mean to do that. Yeah. Let me. Okay. Mm-hmm. Removes the reference binding. Oh. Max valid strings is fib 14. 1,000 is sufficient. Safe. Oh, so let's go 400 then. Let's go 380 actually. It was just a guess that I had. I don't need the temporary there. Let me go for this. Let me also saying I don't need this temporary here. Yeah. Could basically just bin string substring. Okay, let's try that. Okay, so mentioned that the number of non-consecutive strings is fib. Kindly explain this thing. Yeah, I was gonna say I'm sure there's theory involved, but I don't really care to delve into that right now. At the moment. Oops. Yeah. Okay, it's relatively fast, but it's not the best. Simple recursive structure, recurrence relation, a sub n be the number of valid binary strings of length n. No consecutive ones. We can derive recurrence by looking at the last character of the string. Ends in 0. If a valid string of length n ends in 0, the preceding n-1 characters can be any valid string of length n-1. Okay. So that's a sub n-1. Okay. Sure. So if it ends with a 0, it can be any. All right. If it ends with a 1, however, the character before it must be 0. Thus, the strings end in 0, 1. And the preceding n-2 characters can be any valid string of length n-2. Rule of the sum. A sub n is equal to a sub n-1 plus a sub n-2. It's exactly the Fibonacci recurrence. Oh. Okay. Interesting. All right. Select the Fibonacci number, we check the base cases. So 0, 1, count as 2. When n is 1, you have 2. N is 2, you have 3. Fibonacci sequence is 0, 1, 1, 2, 3. So n is 2 corresponds to 4. N is 1 corresponds to 3. means that we are 2 ahead of n, so we're f of n plus 2. Oh. Oh, very interesting. Okay, so recurrence is fairly straightforward. Great. How might check the cost efficiently? Knowing that there are only most strings to look at is fine. And I can even use the Fibonacci sequence to derive those strings more efficiently rather than use 2 to the n iterations. However, the cost function seems much more complex. Utilize. Okay. Cool. So we got a 14. We go 0, 1, 2, 3. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's see if they did the math right. 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 130, 144, 220, 233, 377. There you go. Okay. Cool. That's very cool. All right. Absolutely right to be concerned while the count of valid string shows a simple Fibonacci recurrence having a cost constraint. Cost depends on the specific positions of the ones. Breaks the simple 1D recurrence. The cost is not just a property of the length n, but a specific configuration of bits. However, since n is small and the number of valid strings is tiny, you don't need a complex mathematical formula to filter them. The most efficient approach is to integrate the cost check directly into the generation process, backtracking, which avoids generating invalid strings entirely rather than filtering them later. Efficient generation with backtracking. Using DFS backtracking, this allows you to prune early, generate directly, track cost incrementally, update the cost as you place. Okay. Okay. Less is better. All right. Easily handle n equals 20 or higher if k is restrictive, prints huge branches. Cost logic. Okay. So you suggest a branch and bound here. Okay. Backtracking with pruning. Okay. 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 Got it. And this is optimal because the question itself asks the answer itself is already a large set. So it's not really possible. Answer the question without generating that large set. Yeah, I think that's basically it. There's no way to there's no way to really make it faster anyway than a branch and bound. They're saying backtracking with pruning is more accurate, but I would call it branch and bound because it's easier to say. It's less words and less I don't know, syllables or whatever. All right, so we'll say recurse. Let's think of a recursion. It's definitely easier to do what I did instead of trying to come up with a recursion that's quick, easier. I don't know, the recursion. I'm not as sure about this recursion. And actually, this can be like fib of n. So an interesting note about the Fibonacci sequence, we're going to do fib of n plus 2, which is 1.6 roughly raised to the n plus 2 floor. Stood floor. And this also can be, I think stood power is the one. I don't know if floor is the correct. We'll come back to that. Make sure that's correct. But the recursion is going to be, so we have a cost, we've got an index. How can I build my string? So I could have a current string. Results stood string current. And we could have the index of the string. We're going to build it right to left. So the cost is a constant index. I'm not going to make them const. I'm just going to make them index. Let's do cost. Save an index, save cost, save the current string. Got this result. I'm gonna just absorb everything here. Keep it simple. Actually, I probably shouldn't do that. Results, current. This could be just void, actually. And we're gonna have this auto self. Index 0, cost 0, return result. Base case is going to be, there's going to be a few. So if the current cost is greater than k, then a couple things. So we'll say if the current cost is greater than k, then we return. If the index is greater than n, then we return. It should never be greater than n, but just in case. So if the index is equal to n, that's when you perform the check. Index is equal to n, and say if cost is less than or equal to k, then we're going to say result, push back current, and return. In both cases, we're going to return, but we only push back if the cost is less than or equal to k. Yeah. So now we have two options. We can say self recurse. We're gonna say we're gonna build it left to right. So when it's done, the rightmost character. Yeah, the rightmost characters can be placed. So we're gonna say if current dot back is equal to a 0, then we can call this one, which is a 1. We can say current dot pushback, and this also should be preserve. Okay. So this is for a 1. We're going to say cost plus equals, and then cost minus equals. And we're going to have n as well here. We're going to do n minus ix minus 1, and minus ix minus 1, which again, this probably gets optimized. Push back a 1, pop back. That pop that 1 off. Oh wait, excuse me. This is the wrong one. For some reason, went back to the wrong place. Yeah. So this is update the state, recurse, and reset the state. Index increments by 1, and the new cost. Yeah. And actually, we don't need to do it like that. We could just add it right here. This will automatically handle this. Okay, so that's for the one case. We can only do the one case when there's a 0. And for the other case, we can always push a 0, 1 or a 0 at the end. Increment the cost, but the cost is not going to change if we add the 0. So yeah, always push back 0 and recurse. And that's about it. That's pretty much it. I don't think there's more to it than that. Let's give that a shot, see how that goes. That's about it. Okay. I was gonna say, it's like I thought I needed to capture K in here, but for some reason I thought I didn't too. Part of my mind was like, you need K. Another part was like, you don't need K. So I did need K. It's also slightly incorrect. Slightly incorrect. This should be a character, not a string. It's not slightly incorrect, it's incorrect. Runtime error, no! Oh, okay. Well, golly gee. Okay. What's wrong? It's off of index 0. Why would there be a problem here? Why would this runtime error? Something's not quite right. It could be, I don't know, actually. Overflow dinner. Which test case? Let me try to print some output. Sure. Debugging recursive code sucks so bad. It's so bad. It sucks so much. It's one of those things where like you're not supposed to get recursive code wrong because it's kind of really simple on one hand, but on the other hand, it's like if it does go wrong, it's so awful to debug. Oh, I know it's wrong. Okay, that's so. Uh-huh. Okay. Or if current.empty, or if it's empty, then we can push back. Yeah. That's the or ensures it's not empty. Okay, so wrong answer, but at least okay. Not okay. What's going on here, man? This is subtle too. You ready? This is the index now is kind of reversed from how I was doing it before. So I did an extra reversal here, but I don't actually need to reverse this here. That's really subtle. Yeah. Okay. The double reverse, man. The reverse of the reverse. Uno reverse card, dude. All right. No, it's supposed to be so much more efficient. What is? Oh, I got wrecked, dude. It's supposed to be so much more efficient. Just spent all that time with the chatbot figuring out how to make it optimally efficient, and it's like just about as fast as the other one. Oh my gosh. It's annoying. That's annoying. Oh my goodness. No shortcuts. Lower bound. Can't return a list of 300 strings without writing 300 strings to memory. We'll need to count the solutions. Listing them requires explicit generation. Pruning. Zero wasted work. Generates only the valid strings and nothing else. Any other method would do extra work. Complexity O of M. M is the number of valid strings, satisfying the cost constraint. It's M dot N, I think it says. Optimal touch every character of every output string. M dot N plus ON for the recursion stack. Each work is trivial for modern computers, but the approach is theoretically optimal because it matches the lower bound of the problem's output size. Okay. Logically correct and effectively uses backtracking with pruning to generate the valid strings, correctly enforces the no consecutive ones rule, and the cost constraint. There are two minor inefficiencies and one logical redundancy to address. All right, thank you. Thank you for pointing that out. Redundant cost check in base case, check at the start of the function. If you reach this if, it's guaranteed to be less than or equal to k. Good catch. Oh, there we go, 3 milliseconds. Heck yeah. Heck yeah. There we go. Super clever. Yeah, there are like minor things that I miss like that all the time. Not all the time, but I miss those things from time to time. Subtle things. It's not so much that I miss them, it's more like when I look back at it again, I'll see it, but the first couple of passes, I won't see that. I won't notice that that's actually redundant. That is better. Pretty good. Suboptimal branching order. Okay. 1 first, then 0. Placing 1 increases cost and restricts the next move. Oops, shoot. No. Placing 0 is always safe and costs nothing. Optimization, try 0 first. Deeper valid branches faster and keeps the recursion stack lighter early on. Practice negligible. I want to restrict the costs. Restrict the moves more. What? Prune. Oh, that's. Okay. So it suggested that I switch the branch order. Misconception allocates memory capacity but does not change the string size. Starts as an empty string, works fine. Logical size grows from 0. Swap immediately access current index and pushback. You need to resize. Pushback purchase correct. It's not a. So I did it right. So it's not a misconception. Approximation. Yeah. Yeah. Phi. Oh, I forgot to do square root of 5. Oh. Shoot. I did that wrong. I meant to do phi n plus 1 over square root 5. Yeah, that's fine. It's still a good upper bound anyway. I should static cast. I forgot the static cast. Okay. Let me do that. Let me just hold on a second. Let me do a quick calculator here. Calculation, square root 5. Uno momento, por favor. Yeah, I definitely want to do that, actually. Okay, we're going to do divide by root 5. I use stood floor. Maybe I should do static cast. It's probably better. Const int bound, or yeah, it's just bound. Static cast. I could like name the bound, but it's fine. I forgot. So the actual Fibonacci, it's exactly equal to 5 raised to the n, phi raised to the n minus little phi raised to the n, or the golden ratio raised to the n minus the counterpart raised to the n over square root 5. But phi is very close to 1.6. This is pretty reasonable. And it's going to be less than this number anyway, because of the cost part. So let me do it like this. Try this now. Oh, it's still 11 milliseconds, man. Not what I wanted. Okay. So yeah, I think moving the base case from here to here is probably better, actually. Pre-call pruning. Yeah. Tightest possible pruning. Okay. Should prune as early and as aggressively as possible. Current code prunes only when costs after the cost. Strike moves further by calculating minimum possible future costs before making moves. Future costs always 0. Full recursing, logical order issue. 1 before expensive, branch first, cheap branch second. Suboptimal, cost exceed, recurse, base case, and backtrack. Function call just to fail immediately. Pull 4 recursing, order branches wisely. Alright. Slightly late before the function call. Okay. Fair enough. Alright, we'll do that then. That's fair. Let's do, yeah, okay. Trying to get the fastest, trying to get the 1 millisecond or better. So let's do that. Let's do that then. So we'll do, oops. Didn't mean to do that. This doesn't need to be checked at all. If I move it here, we're going to say, since the cost doesn't change, we don't actually need the cost plus x less than k. Yeah. Yes, something like this. I kind of prefer to do this. It's a little more clear that what's going on here. Yeah, the cost doesn't change here at all, so I don't need to worry so much. Like, and then so prune a little bit earlier. That's pretty clean. The code, it's overall pretty clean. It's actually really clean. Although this is not so clean. This is not as clean. This is maybe a little less clean. I suppose I should do this. Keep it on one line. All right, let's see if it's still correct. There it is. Okay. Okay. 6 milliseconds, a little bit better. It's reasonable. It's better than the 15 and 11 that I got before. We'll try one more time. I think this will get me the 1 millisecond or better. No, 7 milliseconds. Yeah, this is actually pretty tight. Optimally efficient, key strengths, correct logic, redundant checks, reservation, safe approximation. It's more precise, efficient. Yeah, it doesn't. The thing is, you don't need the full golden ratio because there's a couple of reasons. The first one, oh wait, no. Actually, you do want. I could do 6.2. It's probably better. 1.6 is fine. The other issue is here. The thing more important here is that because of the cost element, it's going to be a lot less than this power. It's necessarily going to be significantly less. So, okay, so it says it's optimally efficient. All right. For some reason, not getting 100% on. Yeah, it's close, but it's not 100%. It's really close, but not quite. Output ordering and reservation overhead. Uh-huh. Mm-hmm. Could just do 380, I guess. All right, we'll just do 380, see how it goes. I don't know if that's going to be better or worse. Doesn't seem to matter. Okay. By value, slightly faster for primitive types. Oh, okay. Can I do it like that? I don't know if that's correct. Oh, it is. I can do it like that. Huh. Oh, it is? Oh, it's a lot faster. Oh. Capturing value is faster. I see. Should know that. I've been told that before. I just forgot. 100% solution. I did 380. Yeah. Close. It's not 100% though. What is 1.64? What's up, Vedant brother? Vedant Bothra. Golden ratio. Here, I'll show you. I will show you. The relationship between the golden ratio and the Fibonacci sequence is one of the most famous connections in mathematics, defined by convergence in a precise closed-form formula. The golden ratio, phi, is the positive solution of the quadratic equation, x squared minus x minus 1 equals 0. So phi, which is 1 plus the square root of phi over 2, is approximately 1.618033 ... possesses the unique property that phi equals 1 plus 1 over phi. Convergence of ratios. As the Fibonacci sequence progresses, this ratio of consecutive terms converges rapidly to phi. Limit as n approaches infinity of f of n plus 1 over f of n is phi. So it shows it's phi. By n equals 14, the ratio is accurate to 4 decimal places, approximately 1.6108. 377 over 233. It's approximately 1.610802. This happens because the recurrence, it can be written as fraction f of n plus 1 over f of n equals 1 plus 1 over f of n minus 1. If the ratio converges to a limit L, then L equals 1 plus 1 over L, which is the defining equation of phi. Actually, this wasn't what I was thinking, but it has to do with the closed form solution for the Fibonacci sequence can be represented as phi raised to the n minus little phi, where little phi is the negative solution to x squared minus x minus 1 equals 0. And you could do phi to the n minus little phi to the n quantity, that whole thing divided by the square root of 5. That's the closed form solution for the Fibonacci sequence. So because little phi is roughly 1.618, etc., or big phi rather is 1.618, etc., and then little phi is a small negative value. Little phi, as n gets larger, is vanishingly small. So the Fibonacci sequence is more accurately approximately phi to the n over the square root of 5, rounded. I think you have to round up, actually. Sometimes round up, sometimes round down. I'm not sure. Depends on, I think, phi, if it's positive or negative for n. So I think you just round the number. But in this case, I just rounded it down every time because, and I use slightly smaller number than phi because the cost function is going to ensure that some of the solutions aren't going to pass, meaning this is necessarily going to be less than the Fibonacci numbers anyway, and probably considerably so. So that's why I use 1.6 instead of golden ratio exactly. And then this is Bennett's formula. This is what I was saying. This is phi to the n minus little phi to the n. And then the 1 over phi to the n becomes negligible very quickly. Leads to the approximation used in your code. Rounding this result to the nearest integer gives the exact Fibonacci sequence greater than n greater than 0. Yeah, it's Bennett's formula. Yeah. Yeah, the 1 minus phi, by the way, here is called little phi. It's the reason why you can do that is because this is technically the solution is 1 plus or minus the square root of 5. If you subtract 1 from this, you get the inverse, the opposite. Yeah, which is 2 over 2 minus this gives you 2 minus 1 is 1. Minus the square root of 5 is negative, so you get 1 minus the square root of 5 over 2. Yeah, it's exactly equal to just 1 minus phi. So yeah. Correction to your code, estimate the upper bound, this direct implementation of Bennett's formula, constant index shift, precise value ensures resolution accuracy even for larger n, prevent potential reallocations. Yeah, but I'm not going to have any reallocations because it's because of the recursion back to pruning, we're not going to ever get to phi, or not going to ever get to that to the Fibonacci amount. So yeah, it's pretty close, but not quite 100%. Whom are you teaching to? What's up, 2V X? I was answering Vedant Badra's question. He was asking about where did this 1.6 come from in the code that I had, and I changed the code, but here I'll show you what I had before and what the reasoning was. They said to just remove all that anyway, and I was like, oh, maybe that's right call, but this is what I had in the code. I had 1.6 raised to n over n plus 2 divided by square root of 5. It was a Bennett's formula. Trying to be clever there, but actually it was just slower than just using 380 straight out. Yeah, for some reason I'm not getting the 100%. 100%. 100%. All right, let's try one more time to see what the AI says. Okay, getting very close. At one point, I had 3 milliseconds, but the 100% is 1 millisecond. I think it's about as good as it's going to get. I think I shouldn't spend too much time trying to get the 100% solution. It's pretty darn close. It's probably about as good as it's going to get. What is that? This one. So here you go. This is what. So the relationship between the golden ratio and the Fibonacci sequence is one of the most famous connections in mathematics, defined by convergence and a precise closed form solution. So for this question, the Fibonacci sequence comes into play. And that's why the golden ratio comes into play. And then it gives an explanation. So you can show the Fibonacci sequence is going to be equal to this. Golden ratio raised to the n minus 1 minus the golden ratio quantity raised to the n over square root of 5. And then this smaller part becomes very small very quickly. And so you can just round this expression. And then I also modified the golden ratio from 1.6818 to just 1.6. And so, yeah, that's what's going on there. Last millisecond, got 1 millisecond. You eliminate the overhead of pushback, pop back, and empty check inside the recursion. Fastest approach is to use a pre-allocated string or character array modified by index directly, so its memory management overhead entirely and simplifies the consecutive check to a simple index loop. Optimization for 1 millisecond, direct index assignment. Okay. Current index equals 0. Oh, I see. Remove empty. Okay. Pass string by reference. Sure, the result vector is the only thing being written to. The current path string is just a reusable buffer. Oh, I got 100%. Okay, never mind. Oh, that's a good idea. However, I just got 100%. That's 0 seconds. So I can sleep easy tonight. All right, we did it. We got 100%. Beautiful. 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 Okay. Not only logically correct, but it beats 100% of submissions at runtime. Oh no, actually, I didn't add the direct indexes. Although that's would probably be an improvement too. Exactly. Copy or prompted code. All right, cool. So there you go. It's even more impressive. Algorithmic optimizations were the true game changers, not just the micro optimizations. Pruning dominance, small input size, compiler magic. Cleaner, It's already so efficient. Runtime. Got to hit the measurement floor. Awesome. Enjoy the 100% rank. Thank you. I will. Cool, man. Cool. We did it. We did a team. Where are you from, and are you a professor? What? Not a professor. I'm from the USA. USA. And I probably would have been a professor if I did things differently in life. Probably should have been a professor, man. Things have been so different if I did that. I did get offered to teach as an adjunct once. I think or what, I don't know what it's called when they take you for someone from industry and ask them to teach somewhere. But yeah. Oh, I was a teaching assistant at one point, so not a professor, but no, I've been programming for a long time. I've been programming since I was like 12 or something like that. So like 12 years. No, excuse me, 22 years. 22 years. 12 years, 22 years. Yeah, a little more than that. A little more than 12. Yeah, I've been programming for a long time. Count pairs that form a complete day 1. By the way, if you like the stream, don't forget to give it a like. And if you want to see more of this stuff, you can give me a subscription as well. Subscribe. And you'll see when I'm on and doing stuff. Count pairs that form a complete day 1. Give an integer array hours representing times in hours. Return an integer denoting the number of pairs ij, where I is less than j, and hours of I plus hours of j forms a complete day. Complete day is defined as a time duration that is an exact multiple of 24 hours. For example, 1 day is 24, 2 is 48, 3 is 17, etc. Okay. Denoting the number of pairs such that the sum is an exact multiple of 24. Okay. So one way to do this is to use a frequency map. Take all of the numbers and take the modulo 24 and put those into a frequency map. And then I could run through the frequency map at constant time in 24 iteration, parts, and count the this number. So okay, this would be a pretty relatively efficient way to do it. Frequency. I think this is probably about as good as it's going to get for this one. It's going to be x mod 24. And then we're going to say int I is 0, I is 24, I. Int result is 0. Return results. And we're going to say well, it's really like 13, right? Let's even do 12. Frequency of I plus frequency of 24 plus I. So I'll go 1 to 11, and that'll give me 11 plus 13. And then frequency of 12. It's not going to be 2 times the frequency of 12. It's going to be it's going to be frequency of 12 paired off with itself a bunch of times. It's going to be something like this. Also, let me just check a few things before I submit this. It's only 100, so it's not too bad. But the hours values can be very large. Although once they're modulo 24, it's a lot easier. What do they want for the numbers? The output? Okay, just the count. So there is an issue here. If it's +1 or -1 here, that's the question I have. +1 or -1? I think it's -1. So if I had 3 different numbers, 12, 12, and 12, I could pick one with two other ones to the right, then the next number I'd already paired it with something, so it would be 1 to the right, and the last number was already paired with everything, so it's going to be 2 plus 1 is 3. If I did, so it'd be 3 times 2 divided by 2 is 3. Yeah, it should be minus 1. Sometimes that gets a little bit confusing. Runtime. Okay. Of course. Oh, there's also a mistake here. Yes, slight error there. I think all of these are just alone. Forms a complete day. Pairs. Okay. So actually, I think we just skip I is 0. We just skip I is 0. Wrong answer. Okay. Output 1, expected 3. Oh, no. 0 is very similar to this one. No. Oops. 0 is very similar to this one. Yeah. Just can't pair it with anything else. Oh. No. Wait, what? So there's one pair here. There's one pair here. Should be 2. I got 3. I don't know if this is multiply or add. I think it's multiply. Yeah, it's multiply. That's my mistake. Yeah, okay. Slight variation on what I was thinking. All right. Let's add like 3, 3, 3, and 21, 21, 21, and then 12, 12, 80, some other stuff. Oh, yeah, these numbers could be big. They could be in the billions. Okay. Let's do something like this. Oh, great. What's up? Yeah. Oh, I'm sorry. Forgive me. I have a bad habit. Whenever I look at chat, I just want to say what's up. All right, I'm going to go for it. This may or may not be correct. There could be some errors here. I'm not sure. There could be there's a high chance I made a mistake. Oh, I got it. Okay, done. Sweet. Yeah, that's roughly linear time solution. The frequency map takes a little bit of memory. Oh, here we go. Okay, hard. All right, the hard ones are tough, man. Hard ones are tough. Minimum number of increments on subarrays to form a target array. You're given an integer array target. You have an integer array initial of the same size as target with all elements initially zeros. In one operation, you can choose any subarray from initial and increment each value by 1. Return the minimum number of operations to form a target array from initial. Test case so generates that the answer fits in a 32-bit integer. Integer array target. You have an integer array initial of the same size as target with all elements initially zeros. Integer array target. So this is an array. Okay. You have an integer array initial, so another integer array of the same size, all elements initially zeros. All right. One operation, you can choose any subarray from initial with initial. Okay. And increment each value by 1. All right. Return the minimum number of operations to form a target array from initial. Oh, test case so generates that the answer fits a 32-bit integer. Okay. So it's pretty straightforward. You would sort the target array, and you're going to add the difference array, add the differences together. I think that's it. Yeah, sort and add the difference array. Yeah. Oh, never mind. No, I'm wrong about that. Never mind. Can't do it that way. No. Incorrect. Okay. So, all right. Hmm. Okay. I'm not on I'm not on the wrong track. It's just that what happens is if the smallest element, like you're going to do the minimum element each time, but it's going to be the minimum elements of each like subinterval or subarray. And once you've removed the smallest element, you may or may not have you may or may not have like smaller subcases you got to work on. So maybe a recursive solution is what I want. Let's see what it's 100,000 numbers, and it could be up to 100,000. Okay. Okay. So this is a little more sophisticated than just sorting and taking the difference array. What does chat think about this one? Okay. Okay. So I still think I want to sort it, but I think I probably want to keep track of the indices as well. So it's definitely going to go like smallest elements first. But after I subtract 1 from all of these, I end up with 2 and then 4, 3, and 1. And then I could do 4, 3, and 1 down to 3, 2, and 0. And then this ends up being like this has to go straight down to you know what it might be? It might be starting from the first element, I know I'm going to need at least that many increments. And then I can say, okay, go to the next element. If it's larger, then I add the difference and I go up. And then I keep track of how many I have so far. And I keep doing that until I go up, until I go down. So I can keep going a monotonic sequence upwards. And then when I got to go down, then I would say, okay, when I got this 1, that means that these sections are going to be one sort of block. And then I kind of start over at this one. So then I'll be going up again, and I'd have to add 4 again. Yeah. So when I go down, I would reset. And when I go up, I increment. I think that's the way to do it. So let's do it this way. So we'll do int total equals 0. Constant x of target. Or no. Yeah, that's what I want. Total. And then we're going to say total and then current. And we can set the, so if current is less than x, and current equals x, and total plus equals the difference between x and current, and then set current to x. Otherwise, we're going to downgrade current to x again. So we always reset current to x. But we only update it when the current is less than x. How about that? Could try something like this. Yeah, I think this is it. I'm going to go for it. This may or may not be correct. Yeah, I got it. Sweet. Awesome. LeetCode hard, ladies and gentlemen. Got that one really quick. Starting to buffer now. Got that one really quick. So pretty good. Pretty good. I mean, it's 100%. So, I mean, I was going to optimize this, so try to optimize this, but there's not much to optimize there. Awesome. Sweet. That'll make you feel like a genius, huh? Solving a LeetCode hard in like 2 minutes or just a few minutes. given the minimum area to cover all ones, you're given a 2D binary array grid. Find a rectangle with horizontal and vertical sides of the smallest area such that all the ones in grid lie inside the rectangle. Return the minimum possible area of the rectangle. Okay. Horizontal and vertical sides of the smallest area such that all the ones in the grid lie inside this rectangle. Oh, but all the ones have to lie inside the rectangle. Okay. Here's smallest. Smallest is this one. This is not too hard. So basically, the upper bound, lower bound, left bound, and right bound. So top, bottom, left, and right boundary points. They have to be, the left is going to be the minimum. So if we look at each element, each value of 1, then we're going to take each of those to be the minimums and maximums of those row and column coordinates. So row 0, the top is going to be the minimum. So it's going to be row 0. Top of the rectangle has to be at that row. The bottom of the rectangle is the maximum, which initially is going to be 0. But once I see these, it's going to be 1. And then the left bound, we haven't seen the next value yet, but the left will be set to 1, the right will be set to 1. So everything will be sort of set initially. And then when I see this part, it's going to be set left here and bottom here. And the right part will stay here, and the top will stay here. And then when I see this one, the right and the right part will stay there, modify there. So this isn't too hard. This one's fairly quick, I think, fairly efficient to solve. That's going to be the basic way to do it, I think. So we just have int left, right, top, bottom. Then these will start off. They should be initialized to something, but they really should not have any values at all, quite frankly. Because they really should be like a sentinel value initially, because I haven't processed any of the ones yet. So we're going to say row in grid, and then for const auto x in row, and we're going to say, actually I need the indices. I need the indices. So int r0. First, we're going to do m and n. Size and 0. M is the number of rows and the number of columns. So we're going to say left is, so if grid of row column is a 1, then we're going to say left equals std min of left and row. I might want to make these optionals, quite frankly. It might be easier just make them optionals. I need sentinel values here. That's optionals fine. Optional is a little more concise. It's not as good for older systems or older systems, but it's reasonable here. So I mean, yeah, okay. So if not left or left is, I kind of don't like it though. It's too much extra typing. All right, we're gonna do a different way then. We're gonna do a different way. Left and top are going to be larger numbers, and right and bottom are going to be smaller numbers. Okay. So left is going to start off at n, and top is going to start off at m, and right and bottom are going to be negative numbers. Yep, there we go. Those are fine sentinel values. And then now we do left, right, top, bottom. So left and right are going to be min and max of, it's not the row, but the column. And then top and bottom are going to be the rows. So top is going to be the minimum row and bottom is going to be the maximum row. And then at the end of this, we return the maximum of right minus left. Actually, no, it's going to be right minus left times bottom minus top. Okay, let's go for this one. Minimum possible area, I think is what they're looking for. Wrong answer. Okay. Output 2, expected 6. I think they need a +1 in these cases. That's kind of subtle. But I think I need that in order for this to be correct. And that has to do with counting things. Let's do this one. Let's do 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1. And this I'm just going to add zeros. And let's see how chat's doing. Chat's fine. Okay, I'm going to go for it. I'm pretty sure this is correct. The logic is very simple, but coding it was a little bit wonky. Okay, we got it. Oh, that is really slow. That's really slow. It's only got... It only has... oh, it's 1,000 by 1,000. Oh, I thought it was only 1,000 total. Oh my gosh. That's 1,000,000. Okay. Oh, that's a lot more than I thought. Okay. I was like, wait, why is it so slow? Oh, that's why. It's huge number of values and a huge number of test cases. It's a 1,700,000,000 times, or excuse me, 1,000,000. It's almost 1,000,000,000 things. 700 times 1,000,000. Okay. I don't know if there's a more efficient way to do this, man. This is like about it as far as efficiency goes. Literally just visiting the every element in the grid and then setting 4 values based off of that element position. I mean, I could do it another way. That's probably faster. Yeah, you could do it a faster way. There's an optimized approach. Okay, let's try this one. I'm gonna go for it. Go for it. Yeah, it's a little bit faster, but not much. How could I optimize this code? Reach 100%. Okay. Yeah, it's not that much faster. 0 milliseconds. Redundant updates and unnecessary iterations in your current logic. Update every time you find a pixel. Only really need to update left and top, and right and bottom won't be minimal here. Backward loop. Only really need to update right and top. Updating top and bottom repeatedly for the same row in both loops. Unnecessary break logic after finding the first and last one in a row, which is good, but you still perform 4 inside the if. Early exit has no ones, you still iterate it fully twice. Okay, minimize operations inside the inner loop and separates concerns of finding horizontal versus vertical bounds. Okay, so for each row, find first one in the row. If no one found in this row, skip it. Find the last one in the row. Okay. Update global balance only once per valid row. Case with no black pixels. Problem constraints usually guarantee at least one. I think actually I didn't check that. I think the problem constraints do check. It's at least one. Yeah, okay. I didn't even check that. Didn't even think about it. I didn't even think about it. Okay. All right, let's see. I'm gonna try one. So, first one, last m, or n rather. Then we'll say grid. And same thing. First equals -1. Continue. First, and then right is going to be last. And then these are just going to be top, bottom. Yeah. Wrong. Oh, whoops. This is supposed to be out of this loop. Wrong spot. Okay, let's see what we get here. Let's see if this is still correct. I suppose it is. What are the speeds that other people got? 159 milliseconds. Okay. Hmm. Hmm. This is funny. Okay. All right. Oh boy. Okay. It's problem 3195. Current solution is not the fastest. We need to beat 159 milliseconds, roughly. What do you think? Hmm. Current code? No, it doesn't. Hmm. 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 I could try finding each bound individually. I think this might be a faster way to do it. This might be the fastest way is to do each side one by one. Okay, bound separation. All right, so we'll do top and bottom first. So each row, I'm going to say int column is less than n, n, c. And say if row c, then break, and say a couple things. Top equals r. Left and right. Bottom as well. Oh no, we don't have bottom yet. Left is start off as actually left and right don't really help us that much. We'll just say top. And the same thing for bottom, but going the opposite direction. Okay. So bottom equals R. We don't go past the top. And now we can do column checks. So these get reversed. And we're going to say we don't need this anymore. And it's going to be c equals 0 to from row starts at top or starts at bottom, or excuse me, top, and it's less than bottom. Increment the row and say row C. Then we say left equals C, break, and it's a double break actually. So to double break, we would set row equals top, or top plus 1, or top minus 1 rather. So we would set it would break here, and then it would break that one too. And this one is a double break, so this one's going to be break here, break this loop, and then we set r equal to m for m minus 1. It'll increment r, and it'll be too large. Excuse me, same thing here. So to break, we would set c equal to n, or n minus 1. That gives us the left side. And then we can do turn right minus left plus 1 times bottom minus top. And this is going to be top to bottom. That's fine. This is going to go from n minus 1 rather. It's going to be less the left side. Set the right side equal to C. And this is going to be left side. So we double break. M-1 here. Okay. This is a little bit better, I think. Terminates early on all sides. In this case, it's grid of RC. This is also grid of RC. A little different. Actually, these don't need to be flipped inside out. Oh, actually, no. It's more efficient to do this way. Yeah. You want to go column by column. There we go. Not faster, though. Not faster, though. That's funny. That's funny. 254. Jeez, man. Yeah. It's consistently not the fastest. I think, considering taking a break, I could keep going. All right. Sound faster, critical bugs, incorrect results, critical bugs. A go-to. Oh no. I use go-tos, man. Go-tos are crazy. I don't think that's UB. Am I crazy? Am I crazy? It's not UB. Yeah, I was gonna say. I was like, what? Bad practice. Wait, what? Did I make that mistake? Oh, maybe that's why it's so slow. No, it's correct. R equals top. Yeah. No, it's they. Yeah, that's right. R equals n-1. Break the outer loop. Yeah. No, I need to break. No. I need to break the outer loop after. It's a code smell. Hmm. 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 Okay. Gonna use a Boolean check. What's up, Yash? About to be 5 a.m. for me. I woke up to drink water and going back to sleep. Thought I should drop by and say hello and carpe diem. What's up? Heck yeah, man. Heck yeah, man. I appreciate that. Thank you for coming by and saying hello. Heck yeah. Heck yeah. Yeah, it's pretty late for you guys right now. That's actually, I was trying to figure out whether I should stream or not, or when I should stream today, and I was like, I'll just stream, see how it goes. But yeah, I appreciate you stopping by, saying hello. For sure. For sure. Let's do this. Break flag. Or flag. Exit flag, or I don't know. We'll just use a flag. Um, um, yeah, man. Just just doing some LeetCode problems. Um, and doing okay so far, I would say. Kind of moving right along. Struggling to get the exact optimal solutions though, which is kind of annoying. But otherwise doing just fine. Doing just fine. I am gonna need to soon. I'm gonna need to update the context window for this conversation, though. For the okay, a little bit faster for the AI because it's starting to slow down quite a bit. Hello, brother. Good morning. Hello from India. What's up, Darshan? Welcome. Howdy. Howdy. Good morning. Good morning. Good morning. Yeah, there's a lot of folks in India that like to watch, and I kind of feel bad because the stream is. I'm like 12 hours. It's a 10-hour difference. So like when I'm streaming, a lot of folks in India are sleeping. Um, but the go-to is not good. Mm. Uh, go-to. Ugh. Isn't using go-to terrible though? Like I refuse to use go-to. I refuse. 238, 96%. I gotta get all the way down to 159. All right, what did they do for 159? Let's just look. Let's just look and see, man. What did they do? Okay. I'm in, I'm max, J min, J max. Okay. What? What? They literally did what I did initially. And it just worked. Oh my gosh. You gotta be kidding me. Here I am trying so hard to optimize. Oh my gosh, man. Alright, I'll submit it one more time. That's probably it for me. Production software engineering go-to is widely considered terrible and an anti-pattern. However, in the specific context of competitive programming, the rules change completely. I mean, I wouldn't say that. Terrible, yeah. Acceptable tool. No. No. No, no, no. No. I refuse. I need to build good, healthy habits for the future. Not compromise just because a go-to might shave off a few nanoseconds. Present, we're measuring in milliseconds. So it's not better. In any case, as it turns out, the first solution I posted, which is suboptimal, which is not the fastest I have so far, it's exactly the solution was almost exactly that holds rank 1 100% at the moment. Thus, it's likely that they just had fewer test cases, smaller test cases previously. Think my solution now is very fast. Yeah, I think my solution now probably like around 100%, but it's just that not 100%, but it's pretty fast. It's just that I think they added test cases to this problem because I had this one before and it just wasn't it just wasn't fast enough to get 100% for some reason. Healthy, maintainable coding habits is infinitely more valuable than shaving off nanoseconds on at least LeetCode leaderboard. Thank you. Thank you. Oh gosh. Oh gosh, that's funny. Assessment spot on. All right. Flag-based solutions clean, structured, easy, performance reality. Single digit nanoseconds, test case variance relative to other submissions on that specific day, that specific set of test cases. Almost certainly because they added larger, more complex test cases to the pool, shifting the baseline. Current optimized logic is algorithmically sound and efficient. Stick flag-based or even cleaner lambda-based approach achieved algorithmic optimality for dense grid scan without sacrificing code quality. Far greater victory than fleeting 0 millisecond batch gained via questionable practices. the AI just taking jabs at LeetCode. Subtle jabs at LeetCode. Questionable practices, it says. Oh, it's so funny. Oh, 97.89. That's pretty good. I'll take 97.89%. It's pretty good. Okay, I think the best I got. God, with my revised code is 97.89%, which is quite good. I'll take it. Not exactly what I wanted, but I'll take it. So let's go ahead and Go on to the next question, I think. I was going to take a break, but I kind of just want to keep going. How are we doing? So we got 2 hours in. Okay. Next question is going to be we'll go on the next one. Water bottles 2. Okay, interesting. Read this one in a moment. Just read what the chat had to say here. Excellent result. Effectively optimal in the eyes of the system. Should be satisfied. Statistical noise. Difference is often a few milliseconds. It's like 80 milliseconds in this case. I think it's 159 to 233 is not 80 milliseconds, but close. It's 50 would bring you up to 209, 70, 229, 74 milliseconds. 159 plus 74 is 229 plus 4 is 233. Yeah, it's 74 milliseconds. That's a lot of milliseconds, but that's okay. All right. So it's balanced some things here. Okay, that's fine. 2 integers, num bottles and num exchange. Num bottles represents the number of full water bottles that you initially have. In one operation, you can perform one of the following operations. Drink any number of full water bottles, turning them into empty bottles. Exchange empty bottles with 1 full water bottle. Then increase num exchange by 1. Okay. So I have 2 integers, and I can do one of 2 operations. Drink all the water bottles and turn them into empty bottles, or, well, not all of them, but any number of them, or exchange the empty ones for full ones, and then get the num exchange and increment by 1. Okay. Interesting. But I don't get more water bottles, though. Exchange the empty bottles with 1 full water bottle. With 1? Oh. Cannot exchange multiple batches of empty bottles for the same value of num exchange. For example, if num bottles equals 3 and num exchange equals 1, you cannot exchange 3 empty water bottles for 3 full water bottles. Turn the maximum number of water bottles you can drink. I'm very confused. What? Okay, example 1. You have 13 full bottles, 0 empty bottles. You can exchange 6 number of bottles I drink. Okay. So I drink 13 bottles. I get 13 empty bottles. Drink 13. I can exchange 6. All right. Now I get one full bottle. And I have 7 empty bottles. And I can exchange 7, stuff 13. I can exchange 7 again to get 2 bottles. I could drink 8. I could exchange, I get 13. I could drink the 2 bottles. Oh, that's really confusing. Okay, so I could drink the 13 bottles, and then I could exchange several times to get like a few more bottles, and then I could drink those bottles. And then I could exchange again, potentially. But I think it's optimal to well, I could drink some of the bottles that I've already exchanged in order to make the limit for the exchange to drink more bottles. That's an interesting question. Sort of a math question. What OS are you using? What's up, Sire? How's it going? I actually I don't like to give that information out on the internet. Also, I've been thinking about creating my own operating system, like a custom operating system, because YOLO, but also for security reasons, and also because we have these AI systems now that can like really accelerate code generation, and I get the impression that I could build an operating system solo now, which might sound insane at first, but I'm also highly skilled as a software developer, like to an extreme. I might be arguably one of the best in the world, if not the best, which It's a bit obnoxious to say, but it might be true. It might be true. So I was like, yeah, I don't know. I could just make my own operating system, especially if it's like a minimalist operating system. It'd be like super secure because no one even knows how it works, right? They have no idea what I'm even using. They don't have any information on me because it's totally custom. They'd have no clue. The only thing they could figure out is maybe the hardware, and I could also roll my own hardware too if I wanted to, that's a really sophisticated thing, but it is possible. It's just kind of gnarly. It's pretty gnarly. That's probably a lot harder than running your own custom operatings. I don't know actually which one's worse or harder. They're worse. They're both awesome, but which one's harder is the question. I'd say the rolling hardware is pretty tough. That's a challenging thing for sure. Okay, the table above shows the number of full water bottles, empty water bottles, and value of no exchange. The number of okay, so this is like a math problem. It's like a math problem. And they want to know the optimal number of bottles that you can drink, the maximum number. So here, if we start with 3, 10, so we can do 10 and then exchange 3 and 4 to get 7 into 2. And then we're at 5. And we'd have to drink 2 to get 5 to exchange back to 1, and then we can drink 1. All right, interesting. How big is this number? Okay, the numbers are small, but if the numbers were large, this would get quite a bit more complicated. So I imagine they will ask later on how to do this with bigger numbers. Let me see if I can think of a way to do this more efficiently. Like, for sure, you can optimize you can make this into square root sized steps of num bottles, because you could start with num bottles and then calculate exactly how many exchanges you can do in one step. That's a difference of triangle numbers. That's not too hard. Then the question is, can this ever be less than 1? No, it's always okay. Yeah, so that's a difference of triangle numbers. That's not too hard to figure out how many bottles you're gonna have next, the next iteration. The number of bottles you get, so that would basically, because it's a triangle number, it's gonna be approximately, you're approximately gonna take n and then convert it to square root n, and then convert that to square root n. So you're basically raising it to a power of a half repeatedly, taking the square root repeatedly, which is actually quite a bit faster than dividing it by 2. So it's actually faster than logarithmic time to simply calculate the number of triangular iterations and just repeat that several times. So it's actually faster than a logarithmic time algorithm to do this sort of directly, to kind of just optimize the if you just optimize the triangle number step, it's actually very fast. So it's not constant time, but it's still really fast. It's like logarithmic time, faster than logarithmic. It's going to be repeated square root operations rather than repeatedly divided by 2, which is very fast. That is a very fast algorithm. So we'll use a while loop. So we'll do for, we have int result equals 0. We're gonna say n. We're gonna make this n. N is greater than 0. We're gonna say results plus equals n. Then n is going to be equal to, we're going to say num exchange. We're going to say exchange. So it's going to be how many triangle numbers are required Actually, I need to calculate this correctly. It's going to be it's got to be like x times x plus 1 divided by 2 minus ex times ex plus 1 divided by 2, and actually subtract 1 there. This has to be greater than or equal to n. This has to be largest x such that this is less than or equal to n. Yeah. That's what we're looking for. Then n equals x minus ex plus 1. Yeah. Interesting. Also, how's chat doing? So that's not so obvious, huh? Is that right? I think so. If this triangular number is going to be the sum from 1 to x, including x, subtract the sum from 1 to ex, including ex. Oh, no, not including ex, so I subtract 1 there. And then the number of times that I'll have iterated will be exactly the number of elements in that range inclusive. So x minus ex plus 1. Yeah, that's correct, but how do I calculate x? Well, I could use the quadratic form, so x squared plus x less than or equal to 2n plus ex times ex minus 1. The largest value, if it was equal, I could figure out what the value of x is, and then the largest value would just be the floor of that. Yeah, could set it equal. Then we would say x squared plus x minus 2n minus ex times ex minus 1 equals 0. X equals negative b plus or minus the square root of b squared minus 4 times 1, this is a, times c, which is negative 2n minus ex, ex minus 1, so ex minus 1. Oh no, there's a square root there, yeah. And then that's all over 2a, which is just divided by 2. So it's not going to be the subtraction one, it's going to be the plus one, because it's going to be positive. Square root of 1, it's going to be plus 4, so 8n plus, so multiply negative 4 by each of these, so 8n and 4ex divided by 2, ex minus 1. Square root of that divided by 2. Okay. And that's just going to be floor, or just static cast. Static cast that to an integer. Divide by 2. I don't think I should bit shift, actually. I think I should just divide by 2. Yeah. And this is going to be 1 plus 8 times n. Yeah, current value of n plus 2 times ex times ex minus 1. Yeah. Yeah, I mean, I could just divide by 2 normally and let that be, but I think this is probably more accurate if I do. It might be better to do it this way. Okay. And then n equals, as I said, x minus x plus 1. Any problems here? Yes, there is an issue. Ex has to update to x plus 1. Yes, I think that's it. And then return result. As I mentioned, that should give me an iterated square root algorithm, this time algorithm. And just gonna make that a 1, I guess. Maybe a 0. I don't know. Start at ex. I don't know what that should be initially. Wrong. Okay. Output 13, expected 15. Ouch. Ouch. Okay. All right. So what is x? Five. What is ex? It's 3, right? Starts off at 3. No, it's 6. Oh, that's not correct. It should be 2, or it should be x should be 7. X should be 7, and then minus 6 plus 1 is 2. How come I don't get 7 here? How come I don't get 7 here? Literally just square root part. Literally just the square root part. I want to know. I want to know what's going on here, man. Where's my math? My math is wrong here. 11.8452. Okay. N was 13. So it's 1 plus 8 times 13 plus 2 times. At least this was 6. My algebra was probably wrong somewhere. It's a good chance I did something wrong. 6 times 5 is 30, 60 plus like 101 or something. 30 plus 101 is 131, 132. So it's somewhere around the square root of 132. So somewhere between 11 and 12 minus 1. Yeah, I got 11 point something, right? 11.8452 minus 1 is 10. Divided by 2 is 5. Something's wrong. Okay. Multiply both sides by 2. We get x times x plus 1 equals 2n plus ex times ex minus 1. Okay, then we subtract both sides. This becomes c A is 1, B is 1, C is this part. Negative b plus minus the square root of b squared minus 4ac becomes positive. Multiply by 4. Yeah, this divided by 2 ends up on the outside. This in here is divided by 2. I kind of forgot that, but that's all right. This also should be x divided by 2 square root. This should also be the whole thing divided by 2. Yeah. Okay. I think I translated that correctly. Yeah. Looks okay. It's the wrong answer. All right, so what is this expression? Ex times ex minus 1, 6 and 5. So 6 times 5 is 30. Let's do the math here. X squared plus x equals 2n plus 30. 2 times 13 is 26. It's like 56. All right, so x squared plus x minus 56 equals 0. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Sweat over here, man. Sweat. So it's just gonna be plus because we're not gonna use negative solutions to this. So 225, square root of 225, which is actually pretty interesting. Yeah, that's 225. That's it is a square root of something. I think it's 15 squared. 15 squared. Yeah, it's 7. It's exactly 7. What? How did I get this wrong? I didn't get 225 when I calculated this. That's not what I got. This should be 225. Something's wrong. So this ended up being 60. So it was 30 times 4 is 120. And the other part is 26 times 4, which is 104. 104 plus 120 is 224 plus 1 is 225. Yeah. What? What is wrong? That is 13, right? What is happening? Why didn't I get 7? What's going on, man? Yeah, 15 squared times 15. 15 times 15 is 150 plus 75. That's 225. Yeah, it's 15. So this should be 15 minus 1 is 14. 14 divided by 2 is 7. This should be 7, not 11 point whatever. I did something wrong in my math. Okay, x squared plus x equals 2n plus ex times ex minus 1, and then subtract, and then multiply by -4 becomes plus 8 plus, oh, that's what's wrong. Oh, that's subtle. That's my mistake. Oh, okay. Gosh darn it. Aha. Aha. Oh, it's always when you the mental math, man. It's always the it's still wrong, but better at least. Oh, that's a bummer. That's bad. That's bad, okay. It's real bad. I'm not sure it's supposed to be rounded up or rounded down. It might be a rounded down, rounded up rather. Okay, so now for 10, I do 3 and 4. I should get x equals 4, which I did. And that puts me at 3 bottles that I could exchange and 2 bottles to consume. So 3 and 4. So it's not the difference. We're going to actually increment. We're going to increment by this amount. Excuse me. We're going to. Okay. So I do need like a bottles amount in between. All right. All right. So it's gonna be bottles instead of n, and then the n equals bottles plus this amount. Oh, that's confusing. Hold on. Hold on a minute here. Wait a second. I think I need another variable, but I'm not sure what to do with it. Okay, hold on. So we have the result. We accumulate. We have n. We drink all of n, and then we have 0 bottles left. Now, when I process this here, n becomes something more, and that's how many bottles I was able to get. But here's the thing, I have leftover bottles. So bottles is 0. And we're going to say n is the number of bottles we exchange for. Bottles is going to be so constant amount is this. The number of bottles left is going to be what we have, n minus. So actually, it should be n minus a certain part plus the amount. So we update n. Yeah, we don't need the bottles though. Going back and forth here with this. This is going to be actually exchanged. Could do exchange rate or EXR instead of EX. It's confusing, I know. Excuse me. Exchanged. So this is going to be the difference between the triangle numbers. Okay. All right. So that's the total number of bottles exchanged. We're going to say n minus the bottles exchanged plus this amount. And then we update the exchange rate to x plus 1. Okay. That is confusing. And it's not that easy to grasp all that. I think that's right. That's how we do it. TLE. Now we TLE. Okay, great. All right. Hmm. Could add a break in here too. We just say if the exchange rate is greater than n, then we break. Okay, I got 16 now, but it was supposed to be 13. All right. So 10 bottles, we exchanged 3 and 4 to get down to 5. So we drink 10, exchange 3 and 4 of the 10 to get 3 plus 2 is 5. This is wrong. Yeah, I think I'm making some kind of logical error here for sure. Okay. I have the right idea, but I'm doing it wrong. So let me try again. So drink all the bottles, and here is you increment the result. We drank all of them. Now we say exchange some of them. So X gives us how many we can exchange, or what the new exchange rate's going to be. And we can get the amount that was exchanged. It's going to be X minus exchange rate plus 1. If our new value of n is greater than the exchange rate, then we can just break here. Assuming it's not, then we exchange a certain amount. Now we have bottles left over, which would be after we exchanged some bottles. Or if it's less than the exchange rate. So it's really not n, it's going to be bottles. Let's do bottles instead. It's easier to think about it like bottles. Or empty bottles. And then we can say, hey, bottles plus equals n. N would be 0 now. So the amount is how much n is going to be. Add this amount to n. And then the number of bottles is going to be subtract the exchanged amount. Okay. So you get the amount that was exchanged. We can figure out how many were exchanged. We could decrement the number of bottles. We can set n to the amount. And then the number of bottles left over. Okay. And the exchange rate updates too. That might be easier to think about it that way, to introduce another variable for the bottles. Keep track of that. Still wrong, but easier to think about for sure. Okay, so let's print each of these. Debug x. Let's do a few of these. Let's do x. Let's do bottles. Let's see the exchange rate. Exchanged. Amount. This could be like new bottles or something. Let's start with that information and see what I can get there. Whatever is wrong, it's not that easy to see. So at first we have 10, n is 10. We say x is 4. So exchange rate was 3. So exchange 3 and 4. So you have 3 bottles left. Exchange 7. Amount is 2. So we still have 3 bottles left over, and we have an amount of 2. And then here we say x is 5, but bottles. Oh, I know it's wrong. This is also, yeah, I forgot to update. I know it's wrong. It's no longer n, it's going to be bottles. That's what's different here. I made that mistake. We're trying to, of the bottles we have, we're trying to figure out how many we can exchange. There we go. Yeah, that's okay. The reason I'm doing all this is that I think there's an answer, is a question later down the road that's more, has larger values. And I'm curious if I could solve that question here. So I think it's only 100 to 100, but we can do like larger numbers, I guess. Let's try a few different numbers here. Let's see how this goes. All right, looks like it's correct. Let's try this. It's right. Okay, and it's very efficient. So you could simulate this directly. That technically works, but it's not as efficient as calculating it with. How are we doing? I'm wondering if I want to take a break. I could keep going. You could compute this directly, but it's not as efficient as the algorithm that I just gave. The algorithm that I just gave would be iteration of square roots in terms of how much smaller it becomes, and n becomes square root size each iteration. And so if you had much larger values, then this code would work for that too. Let me see if there is actually a water bottles. Let's see if there's a harder one, larger one. Excuse me. Water bottles. So I just did water bottles 2. Maybe there's a water bottles 3. No, it's not. No, there isn't. They don't have a harder one. Although that's a really efficient way to do it. Okay, interesting. What is this? Well, okay. All right. Okay, it's fine. So no water bottles 3. was expecting there to be one, but there's not. All right. What is the question? Oh, what's up? That's who I am. I didn't see you there before. Question number. It's 3100. Sorry about that. Just so anyone's curious, you can always like scroll back the stream a little bit to see the question I'm working on. Just FYI. Okay, so let me go ahead and keep going here, I guess. I'm tempted to take a break. I might want to take a break and then come back and do another like hour and a half. I was gonna do a full 4 hours straight through, but maybe it's better to take a break. So I think I'll take a break here. So it's about 2 hours and 2.75. Say 2.75 hours. So thank you all for watching. That was an interesting question. That's probably a good spot to stop for now. Just gonna take a break, go get some like food, I think, and then come back, do another hour and 15 minutes or so, hour and 30 minutes.